Good day. My name is Gabriel, and I am here to present the update regarding my project currently entitled Identifying Road Network Congestion Hotspots, a case study of Bonifacio Global City. Congestion has been an issue within developing countries. It is currently defined as a property of transport supply which arises when the demand levels for transport approach the transport system capacity, meaning there are a lot of actors or agents who would want to use the transport system and it's exceeding beyond what is capable of providing. The other instance is when the time required to use the road capacity increases well above average under low demand conditions. Let's say there are not much agents who would want to use the road network, but still the time required to traverse the network is way above average. This pushes for further research in congestion modeling. Congestion modeling has evolved over the years in searching for satisfactory and universal ways of describing and analyzing congestion. Researchers have looked into different approaches such as fluid dynamics, complex systems, or even graph theory in order to visualize and analyze traffic congestion. The role of transport planning, which is supported by traffic and congestion modeling, is to satisfy the transport demand given the limited transport system, which is basically to minimize congestion. There have been various work on other major cities globally, such as Seville in Spain, Munich in Germany, and New Delhi in India. In this paper, we focus on one of the busiest business districts in Metro Manila, the Bonifacio Global City. To start the analysis, here is the inventory of data that is being used. First, to provide an unweighted road network, we gathered the attributes from the OSM or OpenStreetMap. The OSM shapefile of the BGC road network has the following attributes, which can be used for the analysis: directionality, number of lanes, type of roads, and even the speed limit. On the other hand, we also have the traffic jam data of BGC. With the rise of different mapping applications, these applications with the help of the GPS technology can now capture data up to the road segment granularity. In this case, we can now measure the speed in meters per second, the delay in seconds, length of jam, and level of congestion up to the road segment level. The overall approach for this project is to use the network autocorrelation, which is the dependence of variable values on given links to such values on other links to which it is connected in the network context. From a spatial autocorrelation perspective, we basically shift the weights matrix from a node contiguity matrix into a link contiguity matrix. This could also help us identify some hotspots where each of the links are highly correlated with each other, which can be used for further causal inference analysis. So what had happened? First, I was able to assess the overall complexity of the BGC road network using node clustering coefficients and edge centrality. We can see here that the nodes on the entry or exit points of BGC and the inner block intersections have high clustering coefficients, shaded in yellow. This means that these nodes may have similar attributes that can also be a starting point where to pinpoint congestions. From an edge centrality standpoint, we can see that most of the road networks within BGC are highly connected with each other. The extreme roads are shaded in purple or red, while the roads at the middle, which is basically the center of BGC, are shaded in yellow and orange. Secondly, I was able to aggregate the traffic jams data to a date-time segment granularity using averaging and overlaid it using quantum GIS on top of the unweighted network to simulate traffic jams evolution throughout the day. The pulsating effect in this animation corresponds to the traffic peaks within the business hours in BGC. If we look closely into some smaller road segments, we can also see how each of the jams flow or transfer or affect other links preceding or after it. This gives us a soft confirmation that some of the road networks are contributing jams onto succeeding segments or is highly affected by its preceding segments. What would be next from this? First, we need to further aggregate the jam data to an hourly level to reduce the number of data points analyzed. The animation previously shown is animated at an hourly level compared to the date time at the minute level. After that, we would love to join the traffic jam data with the unweighted network to come up with the weighted network. Since we don't have the data for all of the road segments, we have to interpolate the speed for the rest of the road network. To perform the interpolation, we would have to use the speed from the traffic jam data together with the speed limits of the connected segments. Once we have all of the speed for the entire road network, we can now perform the network autocorrelation to identify possible congestion hotspots. We would then compare the results with another run of edge centrality using the weighted network. If time permits, we would extend the scope of the project to perform a spatiotemporal autocorrelation. But for now, we will be using the temporal data to see the evolution of the traffic jam clusters from an animation or simulation standpoint within the day. That is the update of the project. Thank you for listening and have a great day.